So let's talk a little bit about time-invariant linear systems. And intuitively speaking, they are the systems that don't have a built-in clock. So basically it means that we can't do things that like check what time it is right now and do something depending on the value of t. That might sound a little bit imprecise, and it is, and I will show you in a little bit what it means more precisely. The easiest way to define time invariance is to first add some terminology. Let's look at this little picture here. So let's take a real number, usually a positive real number, and look at the following system that for an input signal f of t outputs the same function but where t is replaced by t minus a. So basically that's a system that the time delays the input signal by a seconds or whatever unit t is measured in. I'll leave it as an exercise to check that this is a linear system. I should probably say a few words here about causality as well. I said let a be a real number, usually a bigger than 0. Well, if we would allow negative values of a, this would still be a linear system, but with a negative time delay. And mathematically speaking, there's nothing strange with that, but physically speaking, it's very strange, a very strange system, because if you have a negative a here, a negative time delay, then this system somehow magically knows what will happen in a little while. So if you input the signal f, you get out a signal f showing how f will look like in 10 seconds from now, something like that. And that's something we don't really know how to build in practice. We haven't invented time travel yet. So systems that look ahead in the future are called non-causal systems, and those are, as I said, very difficult to build in real life. Sometimes it makes sense to study non-causal systems anyway, but most of the systems you will find in applications will be causal. So a causal system then is a system, a linear, let's say linear system, such that the output signal only depends on f right now and earlier values of t. So in particular, if you send in an input signal that's 0 up until now, or up until a certain point in time, then the output signal will also be 0 up until that moment in time. Anyway, this time delay system for a positive is then a linear system. And a time invariant system is a system that commutes with time delays. What does that mean? Well, it means that if you have a linear system S and you plug in an input signal F and then you time delay it, you will get some output signal, let's say Y. And this will be the exact same system as if you first time delay the input signal and then pass it through the system S. So a time invariant system is one that commutes with all the time delay operators, so all the time delay systems. Let's check a couple of examples. We return to our favorite example from last time, differentiation. So here, let me remind you that S here is the linear system that maps an input signal f to its derivative f prime. Then, if you first time delay the signal f, then you will get the function f of t minus a. And if you take the derivative of f of t minus a, it's just f prime of t minus a using standard rules of differentiation. And if we do it the other way around, first differentiate, then time delay, then you get a time delay of f prime, which is again the same f prime at t minus a. So differentiation is certainly a time-invariant system. As a second example, let's take this example that also occurred in the previous video, namely multiplication by t. Now, intuitively here, there's we should expect this system not to be time invariant, because in order to multiply the input signal by t, the system must somehow keep track of t. So the system needs a clock to make sure or to be able to compute the output signal. And sure enough, if we take a input signal f, time delay it, you get the function f of t minus a. And if you multiply that by t, so we send the time delay system to system S, then of course we get t times f of t minus a. But if we do it in the other way around, then, I mean, if you first send the function f through the multiplication system, and then you time delay the result, well, you get a time delay of t times f of t, in other words, t minus a times f of t minus a. And clearly, these two outputs will in general not be the same. T times f of t minus a is usually not the same as t minus a times f of t minus a. So many systems that occur in applications are time invariant, and it will turn out that time invariant linear systems have a lot of very nice properties, and we will come back to that in the next video, which is about something called impulse responses. But let's keep this one short and sweet.